Hey guys, welcome back. Alright, so in this video, I'm actually going to start a kind of small little mini-series, if you will, working through from start to finish an example of ordinary least squares regression. And so in this first video, I'm just going to go set up an R Markdown document. We're going to load some data, look at the data, kind of get familiar with it, and then in the next video, we're actually going to talk about the econometric model that we want to run. We'll estimate a least squares model, maybe a couple different versions of it. We'll talk about all the different outputs and start to really dig into how can we identify what is a good OLS regression result, what is one that's maybe not so trustworthy, and then talk about some of the things on how to fix it, interpretation, hypothesis testing, all that. So we're going to go from start to finish, everything you could possibly want, hopefully, out of an ordinary least squares regression. So the first thing I'm going to do is I'm just going to open up a brand new R Markdown document here, and I'm going to select that I want HTML, and I'm just going to title this ordinary least squares regression. And we'll use HTML as the output type, and then we'll see the whole thing kind of laid out typically is what you'd see from an R Markdown document. Now I'm going to kill everything from line 12 down. I'm just going to go ahead and just take it and delete it. I really just want this, the YML header, and then this first command starting at line 9. So the first thing I'm going to do actually here is in the YML header, I'm going to add a subtitle. This is something that you can do. It's mentioned in the documentation, but rarely do people use it, and I love to do this because it just kind of helps to make sure I can drill down exactly what this document is about. And then I'm just going to call this example 1 because I kind of anticipate that I'll go through a couple of different examples in this kind of online econometrics course. Now in this first section, you'll see we're calling the package knitter, and inside knitter we're calling a function called opschunk, and then we're going to set some global settings here. You don't actually have to specify the full true here. I'm going to add a few more settings here. The first is going to be warning. I want any warnings that might possibly come up to not print within my R Markdown document. Also additional any messages that come through, I want that set that equal to false. And then usually whenever it prints some results, it prints them inside the R Markdown with a couple of hashtags or pound signs loaded before that. And I don't want those in, so I'm going to set the comment, those two hashtags equal to NA, so basically so that nothing actually gets printed there. Alright, so once I've got all that set, then I'm actually going to go here and we're going to load all of our packages that we want, and all of them that I kind of anticipate wanting here, I'll go on ahead and load those. You'll need to install these if you don't have these. The data that we want is actually going to come from the carData document or package. This is a package that is it's a supplementary package to car, and so this has a whole bunch of data files in it for various different econometric examples. We're also going to want ggplot2, and because I want to be able to group a boxplot later on, I'm going to call the package ggpubr, and this package it's got some really good helper functions so that you can take your ggplots kind of to the next level and group certain ggplots together and things like that. So it's actually a really fun, unique package. If you're not familiar with it, I highly encourage you to check it out. And then of course, because I love to be able to port OLS regression results into a nicely formatted table that's publication quality and ready to go, we'll use the Stargazer package because it's nice and light, and it's easy to use. It's got a lot of neat features right off the bat. Alright, so once we have those packages, usually 9 times out of 10 I'll take all these library commands and I'll actually put them into this initial chunk that's set up here. But since this document is basically meant and designed to kind of serve as an example file or a helper file for us, I'll go on ahead and explicitly put it out here inside of the actual document, and even with its own header for packages. I do this every now and then. Whenever I'm teaching myself something, I'll sometimes just write an R Markdown document for myself, so that if I need to come back later on, then I've got it. But then also, if someone else needs it, or if a student needs it, then great, I've got this document already ready to go, and I can just send it on to them. All right, so great. Let's talk about our data. So the data that we actually want to use for this example is going to be the salaries data set. And this is a data set that has been collected in order to compare salaries of various college professors over the 2008-2009 academic year. And if you want to look in more of this, you can actually load it. If we actually loaded the library over here, let's see, we want carData, yeah. And then we can actually hit salaries. And we can actually see over here now in the helper file, we can see some additional information about that. And some of that information might be actually helpful for us. We can see that in the description, like I said, it's 2008 to 2009 academic year. We have salaries for assistant professors, associate professors, and full professors. And for those of you that don't actually know much about the tenure system, usually your professors that get hired in, they get hired on as an assistant professor. And then after they publish, provide some service, do a good job teaching, the university kind of decides to hold on to them, then they go through that a tenure voting process, and they become tenured and they move on into the associate professor category. Once after you're in the associate professor category for a few years, you increase your kind of academic standing by publishing more, provide more service to the university, continue to do a good job, show yourself to be a good collegial colleague, and then usually around the height of your career, you'll get, in an ideal setting, you'll get promoted into a full professor. And full professors is usually kind of where you stay unless you move on up or into administration. So it says here in the helper file that the purpose of this is to help college administration monitor salary differences between male and female faculty members. So we can see that in this data set we have a handful of different variables here. First off, we have rank. And this rank is going to be whether you're an assistant, whether you're an associate, or whether you're a full professor. So this is going to be what we would call a factor variable. So each individual observation is going to belong to one of these buckets, if you will. Next, we have another factor variable, discipline, where this is kind of an indicator variable that takes the letter A if it's a theoretical discipline, and the letter B if it's an applied discipline. So you can envision maybe if you're in history, then you're very much into a theoretical discipline. But then, of course, if you're engineering, you're going to be fall into the applied. So you kind of have this dichotomy, if you will, depending upon where the actual faculty member works. Now, I'm assuming history goes into theoretical and engineering goes into applied. I don't exactly know all the details about this survey. Finally, or continuing on, we see years since PhD, so you can envision that those faculty members that are just starting out or that more recently got their PhDs, they probably are more likely to be in that assistant professor category. They're also more likely to start out early, so then they're likely to have a lower pay. You would envision that after you've been with the university a while, you continue to get raises, do well through the promotion process, you also continue to get raises. So over time, you would think that the longer you are away from your graduating date with your PhD, then you would tend to have a higher salary attached to that. Next, we see year service, and this is going to be the years actually working at that university. So this variable should capture, it either would be equal to years since PhD if that faculty member graduated with their PhD and then started working at that university and then never left. But in reality, that doesn't tend to happen. You don't necessarily end up staying at the university that you start in. And so it's entirely possible that some faculty members will move on and then after 1 or 2 or 3 jobs, then settle on into the tenure track process. So that year's service is going to have a lower average value than years since PhD. Finally, we have a gender indicator variable. Now, this particular data set only captures a binary gender. So we have male, we have female. We don't have any other non-binary gender qualifiers here. So we're only going to be able to capture then the detail of the difference between those two genders only. And then we have salary, the actual 9-month salary in dollars. Since this is 2008, 2009, and it's just one static point in time, most likely it doesn't say, but I have a feeling this is nominal and not deflated in any way. Since we're not comparing the salary, though, over multiple years, that's not likely to be a problem. If they are going to continue the study over multiple years, which you would think that's likely to be the case, then they would want to make sure we deflate that in some way. But for now, we'll just leave that in however it comes. All right, and then I'm going to kind of get a glimpse and a snapshot of this data. So I want to say, I want to produce the header of this data, and let's set n equal to 15. Great. All right, so I'm going to save this our Markdown document, and I'm just going to throw it here on my desktop, and I'm just going to call it OLS example 1. I'll save it somewhere else later. We're going to continue to work in this document. Like I said, we're just getting started building this for our own selves, and then I'm going to knit it. There we are. Great, so we can see here we have our header information exactly the way we would want it. We have our packages all printed out there, nice and neat. And then we have the actual data loaded. So we can kind of get a glimpse of this data, if you will, a nice little snapshot. So you can see in that rank column we have professors, assistant, associate professors. For disciplines, it's right now looking like we've only captured those that are in the B category, which are going to be that applied discipline qualifier. We can see years since PhD with all kinds of a range of this, all the way from 1 year since graduating with their PhD to 45 years since graduating with their PhD. And then we have years of service, and just as I expected, yeah, we see years of service being less than for each individual observation, less than the years with PhD, or equal to, for instance, observation 13, we can see we have an assistant professor in an applied department. They have 1 year since they received their PhD, and of course they've only been in the job 1 year. I find this whole year since PhD and year since service, as well as the rank qualifier, a really interesting way to examine this, because you have not only this kind of linear progression, or at least a relationship between the amount of time you spend with the university and your salary. You would think, of course, by definition, the more time you spend with that university, the more experience you have, the more publishing history you have since you received your PhD, the higher your salary will be. So we can envision a nice relationship then between salary and either years of service or years since PhD. But of course, we also have this kind of clustering cohort effect as well. So you can also envision your assistant professors are going to be paid relatively less. Your associate professors, you would envision, would be paid relatively more, and then your full professors would be paid the most relative to the other groups. So I find this a nice way of characterizing this data. We see right here at the top, at least within the first 15 observations, we can see of those we only have one observation that's female. That's not necessarily all that surprising, given that a majority of your university colleges, at least here in the United States, there is some disparity among the sexes. Particularly so within applied disciplines, and since all of these are applied disciplines, that does not necessarily surprise me all that much. Sad but true. So, and then we see our salary numbers with quite a disparity of range here. So on the lower end of this first 15 observations, I'm seeing 77,000, but then on the upper end, observation 2, I'm seeing 173,000. So we have quite a good bit of variation happening here among the actual salary data. All right, so let's plot some of this data and kind of get a sense of what our data looks like. Oops, if I can type correctly. All right, so we're going to use ggplot. If I can type, my goodness. All right, this microphone's right here in my way, so that's part of the problem too. All right, so we're going to give salaries data, the whole data frame into ggplot. We have to be careful with this. Normally, you might probably want to be explicit and say data equals salaries, but we don't necessarily have to in this case. But since this is all a data frame anyway, we want to define how this plot looks. So along the x-axis, I'm going to put years since PhD, and I believe that is how that data is expressed. Yeah, years.since.phd. Great. On the y-axis, let's see. I'm going to put the log of salary. I'm going to define the size of this since I'm going to be plotting a geom point. I know exactly what I'm like. Why is it not formatting right? And I'm like, okay, I'm an idiot here because I need to put this inside of an R chunk. Excuse me. Like, that doesn't make sense. Why is it not auto-indenting? That's not auto-indenting because I've not done something right. There we go. All right, so for the size, I'm going to express years sent of service. So as we move along this x-axis of years since PhD, we're going to have also a nice progression of years since service. And I have a feeling this year since PhD and this year since service, these are going to be, this might be a problem point within our theoretical model, because these two variables, if they're included as two independent variables, I would envision these to be relatively highly correlated among themselves. So yeah, but let's just see if the data actually bears that out, and then we'll define the color to actually be discipline. Great. And then we want geom point, and I don't need to specify any additional information there since I've already put all of my aesthetics for how this should look within the main ggplot argument. And then we want to put some labels here. And we'll do years since PhD attainment. And then for Y, we'll put salary. Oops. If you ever forget your quotation marks, you can just select the whole word and then press Shift in your quotes, and it'll actually wrap the whole thing in quotes. Just FYI. And then, which I'm constantly doing, we'll do natural logarithm. All right, great. Now, before we don't actually have to knit this, I can actually say, okay, let me load everything prior to this, and then preview this, and we can actually see the full preview happening within our Markdown document, which is kind of a nice, comfortable way to look at things. So we can actually preview some of this within our Markdown environment without knitting it. So yeah, exactly as we would have expected here. So we see a clustering of our assistant professors happening here early on in their career. Salaries are relatively low. As we move on into the associate professor range, years of service increases, the dots get bigger. We start to capture more people at the associate and professor level happening up here. You kind of hit a peak of optimal salary earnings, and then salaries start to kind of drop off a little bit. Now, this could be a couple of different things happening here, because this is just one snapshot in time, so it's entirely possible that there's been some upward trajectory of some inflation, if you will, in terms of the cost of the average tenure track faculty member happening here. And so you could see a whole bunch of older faculty members that are towards the end of their career being relatively underpaid because the price of a newly minted PhD kind of bids up that price. So the only question is whether this tends to continue as we move forward through time, or if this this whole relationship kind of remains and we kind of send this little arching hump, if you will. I have a feeling you'll probably will see this continue on, even as younger faculty members like myself that are around in this range will be here later on, and this whole scale will shift upwards through time. That's my own hunch, but we'll see if that actually bears out. We can see we have the different colors based on discipline, A being that theoretical discipline qualifier, and B being the applied discipline qualifier. So you can see we have relatively higher salaries among the applied disciplines and relatively more lower ones among the theoretical disciplines, which is not necessarily surprising at all. All right. It's always a good idea to try to plot and visualize your data, especially given what you're trying to explain in a linear framework. So notice that I put along the y-axis my salary data. So my salary data is what I'm trying to explain, and I'm going to explain it with all of the other variables that I have. The rank of the professor, how long they've been with that university, the amount of time they've had since they have their PhD, of course, gender and discipline as well, all thrown in there. And so this is always a good practice, and I highly encourage anyone before they even run a linear regression. It's so easy to run a regression in R, and that's part of the problem, is because it's just easy just to do it and go. But it may be beneficial to stop and think about what we're doing and plot some of this data. Here we can see, based upon years with from PhD attainment, we have this kind of parabolic shape happening here, which means we kind of hit an optimal point somewhere here around 30 years of service, and then we start to taper off. And as a result of that, it may be reasonable for us to account for that within our linear regression framework, and I want to show you one possible way to do that. All right, so let's keep on moving forward with our exploration of the data, if you will. I'm going to include another R chunk, and here's where I really wanted the ggpub-r package, and I may use it later on, but I particularly wanted for this. I'm going to use the function ggarrange, and I'm going to put in 3 ggplot arguments, and I'm just going to separate each one of those ggplots by a comma, and then I'm going to put all of them in one graph, if you will. So we'll use ggplot. I want to, of course, plot salaries, my salaries data, and then I want this to be on my x-axis. I'm going to put discipline. On my y-axis, I'm going to put log of salary, and then I want to color, excuse me, I want to color this, and I'm going to color it by the actual discipline. So the color of this box plot is going to be the actual x-axis itself. And then we're going to do geom box plot. And I don't need any additional arguments there. And so I'm actually going to take this whole ggplot argument, including the comma there, and I'm going to paste it down here directly below that and just change a couple things. So in the second one, I'm going to plot this against rank. And in the third, I'm going to plot it against our gender variable, which was called sex. And then the final argument of this, I'm going to specify the number of rows. In this case, I want 3. And that should be good to go. I think we have everything that we need there. So let me run that. Yeah, okay, never mind. That's too small. So let me actually knit this. And then we can actually show it relatively bigger over here on this side. Yeah, it's not too much bigger, but hey, we'll take it and go with it. All right, so we have three kind of box plots here, and so the box plot shows the distribution of the data based upon the x-axis variable. So in all three cases, we have the log of salary kind of put here. And the reason I took the natural log is because we have quite a disparity of data going all from spanning basically more than $100,000 in terms of the range of our salary. So by taking the natural log, it's a monotonic transformation. It maintains all of the variation, the relative position, but it just squishes it down in terms of the actual variation and scale of that y variable. So as you can see here, we have an observation below 11 and then observations above 12, but I mean it's relatively smaller, so it squeezes the whole distribution of the actual variable itself. But this a box plot will then take this. These are really good with categorical data, not so much so with continuous data, but we have some categorical variables here. We have discipline, we have rank, and we have gender, and so we can actually then separate all the data based upon that categorical qualifier, discipline, rank, or sex, and then plot those distributions, and so we can compare them. Here we can see along discipline, we do have a kind of a shift upward. So the B discipline, which captures that applied discipline range, they have higher. The upper end of that distribution is higher than the theoretical, and the low is higher than the lower end of the theoretical. But right then at the middle, the bold line in the middle of the box is the median of the distribution. The medians are not that far apart, so they're really kind of clustered together. There's looks to be a bit more variance happening along the theoretical disciplines, so we can see more spread. The box is relatively bigger, but just a little bit so than the applied disciplines. The rank is exactly as we would expect. We see assistant professors, and then we kind of move up a little bit, and we see associate professors, then we move up a bit more, and we see the full professors. The variation of the full professors is really surprising. So with the traditional box plot, we have these kind of whiskers popping out of here, and sometimes these are called box and whisker plots. So the lines happening here either capture a 95% confidence interval around the median, or they capture the upper bound of the data. If there's a point that pops out below the whisker, as it does here with the professor rank, then we have at least one observation that's statistically lower than the median around a 95% confidence interval, and it probably is that observation hanging around right there that we saw in our previous plot. And then right below that for the gender makeup, this I kind of find really interesting, and given that that was the purpose of the study and the primary reason for collecting the data, this is kind of telling. So we see that the medians along the binary gender qualifier is pretty much equal with one another. However, the two distributions are skewed in opposite directions. So you have relatively more females skewing this upwards, moving this median upward. And so if you're not at that median and you're below the median, you're likely to be relatively lower or considerably lower than the median. But it's just the opposite for males. For males, you have it's skewed more towards the bottom and less so for the top. And so I find that interesting, even though we have this whole male qualifier group, the shaded box along the first to third quantile, or quartiles rather, it is higher. So yeah, we have some really good data, really interesting data. I think this kind of informs us in terms of our linear model. This gives us an idea of what we can expect. We definitely want to incorporate the rank variable in here. We need to account for this discipline to see if this is going to be something that shakes out to be important to us. And we definitely should include the female male binary gender qualifier in a linear regression framework. All right, so in the next video, we're actually going to take this, allow some of this information to kind of guide us into our linear regression model. We're going to specify our econometric model. We're going to estimate it, and then we're going to start talking about all of the plethora of results that R gives us for that. Thank you very much for watching, and I'll see you next time.